Hello, honors physics students. This is right where we left off as we were talking about an object moving in uniform circular motion. In this case, the object was our passenger in the car making the right-hand turn, where the speed was always constant, v naught equals vf, so we said just set equal to v, but the direction was always changing, so there was an acceleration. We realized the only way for that acceleration to be acting upon the object without it speeding up or slowing down was for the acceleration to point at right angles to the motion. While the direction of acceleration was always changing, it was always pointing to the center, and we gave a new word for that, centripetal. This is a centripetal acceleration, and here's the equation for centripetal acceleration, AC equals v squared over r. Let's go back to our picture here. We think back to previous topics. We know the only way for an object to accelerate is if there's a net force acting on it, right? Sigma F equals ma, and hopefully you remember that sigma F equals ma is a vector equation, that the direction of the acceleration is always the direction of the net force. So in each of these pictures, we can draw that sigma F points this way, or this way, or this way, right? And so even though the direction of the net force is changing, there again is a commonality. All the directions of the net force, they're all pointing towards the center. And so we're going to define centripetal force. It even gets its own symbol, F sub c, just like centripetal acceleration had its own symbol, A sub c, where the c just stands for centripetal. And centripetal force is the net force that points to the center. This is what happens in circular motion. Now at this point, you may be thinking, oh, centripetal force, this is a new type of force. Let's add it to the list, right? We have all these different types of forces that arise in specific situations. Weight, that's the force of gravity. Normal force, that comes when objects press up against each other. Friction force, that happens when an object is dragged or is trying to be dragged across a rough surface. Tension, that happens when there's a string or a cord involved, right? And so let's say we'll add this force to the list. Well, let me be very clear about this. No. Okay, just in case you missed that, I'll do it a little bit louder. No! Don't do that. We're not going to do that because, as it turns out, centripetal force is not a new force. It is not. It is not a separate kind of force. What is centripetal force? Well, it's right here. Centripetal force is net force. So when an object is moving in circular motion or part of a circle, the net force has to point to the center. And so we just added an adjective to this. We call it centripetal force. So to really highlight the fact that centripetal force is not a new force, let's write this. F sub c equals sigma F. That in circular motion, the net force points to the center, so we call it centripetal force. In fact, let's do this. Let's box it in. New equation. This, I think, might be the easiest new equation all year long. You can't mess it up. Well, I guess you could. And in fact, in years past, some students have succeeded in messing it up. But, don't be one of them. You shouldn't mess this up. They are literally the same thing. Now, let's put some things together. Of course, we know sigma F equals ma, so in circular motion, we just slap a subscript c on there, indicating it is a centripetal acceleration. And now we're just going to combine equations. We know from before, a sub c is v squared over r, and sigma F is F sub c, and so we can put these two together into one equation for centripetal force, which is a bit of a shortcut. Once in a while, you might be asked to calculate the centripetal force, in which case you would just use this equation, F sub c equals mv squared over r.